classification. Okay, we have Gini index instead of error rate and have entropy. Okay, we were here, parameters preferences. We were talking about which measure to use in case of classification. Based on some observations that not always error rate is so much sensitive that we can use it while we are going to split decision trees. Instead of error rate, we decided to use Gini index or cross entropy while splitting. Then when you are trying to prune the corresponding tree, then error rate is preferable because it is not so much sensitive. So between cross entropy and Gini index, there is no very big difference in case of decision trees because they are actually ending up with the same decision trees. So there is no big difference which one we are using. And here we have one very interesting idea. This is information gain, how we are using Gini index or entropy when we are deciding how to split the corresponding feature and when we are trying to understand from where to split. So in case of regression, we have the corresponding measure known as RSS. If you remember, we were using RSS. Before split and after split, we were just comparing two different numbers. If after split, you are checking the corresponding RSS for different features for different splits, then the smallest one you are taking as the next split. So in case of classification tree, we don't have this RSS because our class is now are actually categorical. Our outputs are categorical, are classes. So what we are measuring here. So we have before split, we have parent. It means that we are working with some regions in our p-dimensional feature space. So when you have a region and you are trying to understand, are you going to split this region into smaller regions or no? And if yes, which feature and which attribute to use? Or from where to split, how to split. So before splitting, we have domain parent. This is our region. We have such a domain known as parent. After splitting in decision tree, you have left domain and right domain. So here you see IG is standing for information gain for a parent. We are trying to understand, is it reasonable to continue splitting or no? And on the right, we have this information gain formula where you see this I. Instead of I, we can calculate entropy or can calculate Gini index, no big difference. So here we have the parent, Gini index of the parent. So in parent domain, we have different classes. For each class, we are calculating the corresponding probability. Based on these probabilities, we are calculating the Gini index or entropy measure. Then we have left and right domains. Here you see some weights, the number of points after splitting that we will find in the left domain compared to the parent. So when you are splitting your domain, you are actually splitting your observations into left and right domains. Here we are just calculating the weights, the fractions, how many points, the percentage of points that we will have in the left and right domains. then with the corresponding Gini or entropy measures for the left and for the right. So from the preliminary original Gini index, we are subtracting Gini indices weighted for the left and for the right. And we are waiting that after the best split, the information gain will become actually smaller, and we are finding for the smallest value, actually the biggest jump after splitting. And this is helping to understand, is it reasonable to split, and if to split, from where to split. This is actually, in some cases, you can use also as a pruning, tree pruning idea. So when you see that there is no very big information gain, then you are just stopping to split your decision tree. This is also acceptable, and in many implementations, this is applicable something for pruning. So if you remember, in case of decision trees, this pruning technology is very important, because for a training set, we can endlessly split the decision tree and overfit the data. We need to understand where to stop. We need some stopping criteria. And in case of classification, this can be, of course, one of the stopping criteria, together with the idea that we discussed, and we will return to it. So summarizing, so we have Gini index and cross entropy while we are splitting the nodes and growing the tree. When you have very big tree and you are deciding about how to prune, then you can return to this, finally, to this error rate, return to regularization, where you have complexity parameter, and based on some 10-fold or 5-fold cross-validation, decide which subtree should be the best one. So here is one example. We have car seats data, many different features, data frame with 400 observations, 11 variables. Output is actually, why this is yeah, okay. Although the sales here is numeric, I was surprised that we are working with numeric output while doing classification. So idea is here the following. So we are dividing this. You see here we have which one we are taking here. So sales. You see the sales in red. So this is our output, but we are trying to transform it to a categorical variable. That is why you see here we are using, if car seats sales is bigger than 8, then we are constructing new categorical variable with yes and no. So when we have bigger than 8, then we are putting, instead of this new variable car seats high, yes, or we are putting no. So we are transforming our numerical variable sales into high and low sales. When we have yes, this is high sales bigger than 8. If no, then this is lower sales. So by this transformation, we are getting categorical variable and trying to predict this categorical variable either into yes and no's. And you see the corresponding decision tree. On the leaves, you have either no or yes. So it's how we are classifying when a new observation is coming. You are just from top to down following the values of the corresponding features of shelf log, price, income, advertisement, and actually ending up with one of the leaves, no or yes. And this is how we're predicting it. You see, this is rather big tree. many different splits. Then by the same way as we discussed, we have pruning technology with some alpha parameter. By the way, I checked this complexity parameter, how connected with this alpha parameter is just exactly equals to alpha parameter in our implementation. So when you see this complexity parameter, this is exactly our alpha. One observation here, if you remember, we had RSS plus alpha multiplied by the tree size. In this case, instead of this RSS, we are using error rate of our classification. So if you remember, we have a regular problem here, regression versus classification. In case of classification, the objective function is different than in case of regression. For regression, we have RSS, sum of square of residuals, something like an error, because when you are averaging it and taking square root, it is our root mean square error. In case of classification, we have error rate, so the percentage of misclassifications, this is error rate, and here you see we can draw the corresponding graph. Accuracy of the cross validation, which is the same as to draw the error rate, versus different complexity parameters. And as we are trying to optimize the accuracy, we need to maximize it. So we are taking the maximum accuracy with the corresponding complexity parameter. So it's saying how to select the right size for the tree, because when you have the corresponding complexity parameter, you are taking one of the subtrees. And for this subtree, we have smaller decision tree, which is actually trying not to overfit our training set. Not very much small decision tree, but in any case, smaller than the previous one. This is based on the program that I wrote previously in our programming language, but the same things we can draw also for Python. The output, they are visually different. So when you see tree like this, then be sure that it is coming from our programming language. In Python, we have much colorful decision trees, but no matter, the idea is the same. And this is actually the end of our classification theory. Now some comparisons. If you have questions, then go ahead and we will jump into these comparisons. We had before linear models, now we have trees, we are trying to compare them, but if you have some questions, go ahead.
Excuse me, in this model, shell block is a categorical data, yes?
Which one?
Shell block.
Shell veloc is actually numeric. You see it's giving us smaller than 0.5. In this case, all variables are numeric. Let's check. So here we have price shell veloc. Okay, shell veloc is factor. Okay, sorry, shell veloc is categorical variable. So we have bad, good, and medium.
And how we can convert it to the numerical for split
As
learning?
usually we are doing by dummification or by just putting here values. You see 0, 1, 0, 1, 2. So
Yes.
that is why, and here we have also, urban is also factor with 2 levels, no, yes. You see 1 and 2 here we have.
Okay.
And US is also factor, Shevelok is factor. We are just doing factorization, similarly as we are doing it in case of Python.
Okay.
So in Python, we exactly need to transform all our categorical variables into factors. In case of our programming language, it's automatically performing the corresponding transformations.
Okay. Thank you.
So again, it is just splitting. When you see then something is smaller than 0.5, you know the corresponding numerical values. You are just using that. Instead of 0, 1, and 2, you can use bad, good, and medium. So no difference PM. In any case, in case of decision trees or other machine learning algorithms, we always need to somehow perform dummification or factorization of the corresponding categorical variables. So now comparison with linear models. As a linear models, you can remember. So in case of regression, we had multiple linear regression and also lasso and ridge regression. As a classification approaches, we have, for example, logistic regression, which is linear. Also, we have LDA, which is linear. So when you are trying to understand which model is better, so linear models or tree models, so it is natural to come to the first observation. If the relationship between the predictors and response is linear, then of course you are applying linear approaches. Everything is very logical. If you know that the relationship is not linear, then the only way that we can somehow predict the output is to use nonlinear approaches. So we need to remember that decision trees are nonlinear approach for classification and nonlinear approach for regression. That is why there is no choice if you know before that the output is nonlinearly depending on your predictors, then you can use only decision trees, not linear models. And this is visualization of the difference of the trees and linear models. You see 4 different, actually here we are showing classification problems. So 4 different binary classification problems. So green and yellow are different classes, and this black line is the corresponding decision boundary. You see when classes are linearly separable, then of course linear method like linear regression or logistic regression or LDA are working excellently. So you see the first example on the top left one is based on logistic regression or LDA, and the right one is decision trees trying to somehow divide based on our domain stratification or segmentation into domains where you can predict green ones and yellow ones. You see that it is not working, because in case of LDA or logistic regression, we have actually accuracy of 100% because we have any single misclassification. All green points are in the green zone and all yellow points are in the yellow zone. While in case of decision trees, you see in each small region, there are always both green and yellow points. Usually how we are doing prediction based on this figure, when you see that the number of green points is bigger than the number of yellow points in the corresponding region, then when a new observation is coming, you are assigning to the dominant class. You see, for example, when here we have dominant class of green points, here we have small portion of yellow points. The portion of yellow points that you see here will be your final error rate, because you will classify all these points into green points, but actually they are yellow. And you see that in each small region, we have both classes, greens and yellows. And here, for example, when you are returning yellow class, you have a small portion of green points, which is actually your classification error rate. So when you are comparing, you are seeing that decision tree is actually useless in this case. Logistic regression or LDA actually performing excellently with 0 error rate and 100% accuracy. And for the bottom figures, we have totally different picture. In this case, two different classes, green and yellow, are not linearly separable. Although logistic regression or LDA will try to somehow draw a line trying to minimize the error rate, but actually you see that not working. While decision trees, just based on two vertical and horizontal cuts, just giving us 100% of accuracy and zero error rate. So this is an excellent comparison showing that there is no the best approach in machine learning. You always need to understand what kind of data you have and which method will perform better. So usually you are, if you don't know some additional information about your observations, then just try different methods, compare them based on classification reports, accuracies, error rates, precisions, recalls, ROC curves, and try to understand which model is performing better. But actually you know that underlying description is based on linearity of the observations or non-linearity. So this is what we have about decision trees. Now, as a comparison, now some advantages and disadvantages. As usually, all machine learning algorithms have some disadvantages and advantages, so there is no way to escape this problem. So, first of all, the most powerful and important thing for trees is interpretability, because visual perception, when you look into the decision tree, is just excellent, because you exactly understand how your features are split into regions in order to somehow predict your output. And it's very easy to explain to people, even not to mathematicians and not to experts. It's just high level understanding of your underlying data. So trees can be plotted graphically and easily to interpret, even non-experts. It's easy to explain to people. And what is interesting, you already know that they are working well for classification and regression. And also there is no difference, are you using binary classification or multi-class classification problem? So they are very universal. But the biggest problem that we have with decision trees is the prediction accuracy. They are not very much powerful, which is natural, because you know that interpretability and accuracy are very, it's actually saying that it's very difficult to have machine learning algorithm which has both predictive power and interpretability. There is no actually such algorithm, because when you see an algorithm with some bigger interpretability, then know that it is coming due to less power in prediction. So if you are trying to increase the prediction, you are losing in interpretability. Also, one biggest problem with decision trees is that they are very sensitive to your observations. When you are adding some additional observations or deleting some of them, then when you are constructing again the decision tree, it can be totally different decision tree. So they are very sensitive. It means that when you are trying on different observations several times, based on cross-validation to construct some decision trees, sometimes they can be totally different. And don't be confused, it's well-known characteristic of decision trees, the sensitivity. So now the idea that we are following, we are trying to increase the power of decision trees. We are trying to improve them. Of course, we will lose in interpretability, but however, we need more power, and we will apply different technologies in order to increase the power. So there are different concepts, very general concepts in machine learning, and we will try to apply one by one these approaches. Yes, of course, go ahead with questions.
You said it's natural that decision trees are not good with predictions. Where is that intuition coming from? I mean, I kind of I'm guessing, but can you like say specifically where is the intuition coming from that they are like bad predictors?
Interpretability versus predictive power. If you have very easy approach, which is very easy to explain to people, expect low power for that method. This is just general intuition. Because you will never find very powerful. Always remember neural networks, very powerful, very flexible. Never you can understand how they are working. Never you can explain to your customers and users how you are predicting your output. In case of decision trees, everything is very simple. Visually, graphically, you exactly see how decision tree is splitting your features into different domains and how it is predicting the observations in each domain. When you see such an easy of understanding, expect something bad in prediction accuracy, in prediction power. This is just the natural law of our universe. Never you will see both interpretability and power.
Okay, thank you.
Mr. Bohosian, for all methods in the classification, KNN, LEA, QDA, or logistic regression, I think all of them have the power of prediction, yes? Or
Not always.
how does
Logistic regression is a linear approach. It is easy to understand because you have parametric model. You can write down this parametric model, show the corresponding coefficients. For each coefficient, you can calculate the corresponding p-values. So much easier to interpret what you have with logistic regression. That is why it's just a linear, no any powerful approach here. So when you are comparing it is with QDA, QDA is non-linear approach, has more predictive power, but less problematic to explain it to people because you need to understand there are different normal distributions. Within these normal distributions, you have different standard deviations. So much harder to explain to people. That is why, again, when you have linear method parametric model, much easier to interpret, to understand how it is working for your observations, to explain the idea. But in case of QDA and KNN, much problematic. Also, the idea of KNN is very easy. But when you have the final model and saying that, for example, you know K equals 80, saying nothing, although you can theoretically, mathematically understand why. But KNN is standing actually separately because it's very complex approach. In many cases, it's non-linear approach, although the mathematical theory is very easy to explain. But again, in terms of interpretability, when you have a specific application, specific data, and you are trying to understand why, for example, not taking 5 observations in a vicinity, but 80 observations, it's very difficult to understand. We have only higher level logic. Maybe this is connected with some noise in our data. Maybe we have a lot of outliers, but no any further interpretation of the results, why parameter this or that. While in case of linear regression, you have exact model. Finally, you have exact values for the coefficients. And you can just show this formula to different people, say, this is the connection between your features, if in reality, the connection is linear. So that is why always we are giving you this example of neural networks. Just very powerful, extreme power, but no any interpretability, which is, I am again saying that it's natural because there are two different extreme cases, interpretability versus power. Usually as more powerful things you need, as more flexible and complex things you need to use. Much complex means less interpretability. Now going ahead with this, okay, we have also another data here. This is hard data. So let's jump very quickly. You see, I deliberately took very big decision tree. This is actually overfitting of data. You cannot understand what's going on here. Then after pruning, we are getting smaller tree. By the way, I am using another functionality of R programming language here, much colorful decision trees. And that's it. Now we are jumping to different powerful approaches. We have here bagging, we have here random forests, and boosting. Yeah, go ahead.
What does the colors mean in the decision tree?
Colors are showing the purity of your node. So based on some Gini index or entropy measure. So usually you see you have two kind of observations. You see here the description of the nodes. You have, for example, here 37 and 164. This is standing 37 for the first class and it is just saying that 40 minutes passed. Okay, I am sharing the screen. Slideshow playing from current slide. Okay, for each node we have description of two classes. Use the first class is 37, the second class is 164. So decision tree is just trying to understand within this node which class is dominant. So when you see that the second number is bigger than the second class is dominant class, in this case you see some blue colors. When you see this darker blue, it means that the purity is becoming bigger. So Gini index is becoming close to 0. You see here 13 versus 1. So there is a very big dominant second class. It means that this node is rather pure. But when you see light color, for example, 24 and 49, you see that this node is not very much pure. In case of green nodes, why the second one is bigger? Because description is yes, yeah. So wrong description from myself. This is not actually the first class and the second class. This is showing the portion of the numbers within that class versus the overall. So this is only showing the fraction. So when you see blue colors, it is dominant is no. When you see green colors, the dominant is yes. And again, the darker and lighter colors are showing the purity of the node. When you see this dark green, then you see then 7, 4, and 6. This is, I need to check how this information, what does it mean, this information, but I am assuming that it's showing me the error. So within 74 yeses, I have only 6 no's. So the node is very pure. It says that I have very big yes dominance class here. And here you see that we have 59 yes, but this 27 is our misclassification. So usually colors in case of Python and in case of R programming language are showing different classes, how you are predicting no's or yes. And lighter and darker colors are connected with the purity. As darker, then more pure node you have, as smaller is your misclassification error. This is how usually you are going to interpret the trees.
Okay.
And you will see different outputs. In each case, you need to check what decision tree is showing. In case of Python, it's much easier to understand because it's just showing the number of observations within each class. It's showing the corresponding Gini index entropy and the overall number of samples. In this case, we have different outputs. We need to check what does it mean. I am assuming that okay, in any case, we need to check here the form of output.
Yeah, okay, thank you.
But colors are interpretation of the corresponding purity and the corresponding classes. Now about bagging. So we have problem with decision tree accuracy, with the power of the decision trees. And we are trying to apply different classical technologies in order to increase the power. So we have three approaches here. We have bagging, we have random forests, and we have boosting. Actually, bagging somehow is the same as random forest. You will see that it is depending on a parameter. For a specific parameter of bagging, you are getting just random forests. Boosting and bagging are very powerful. Now they are very trendy together with support vector machines, and they are somehow comparable in power even with neural networks, because in many cases they are much easier to train. There is no need to apply GPUs. That is why boosting is very popular with support vector machines. Now recall that we had also one problem with decision trees: sensitivity across training data. So it means that decision trees suffer from high variance. High variance means that you are just changing your data. They are very flexible and they are changing their structure. It's very bad because when you are repeating the same decision tree several times and you are applying cross-validation to understand how to split your features, sometimes you are seeing totally different picture of your decision tree, and it's confusing because you need to start your interpretations from the beginning. So this is the description. What does it mean that it's also very sensitive? When you are randomly splitting the training data into two parts and fit decision trees on both parts, the results could be quite different. This is how they can be confusing. So the main approach which will somehow decrease the high variance, you know that it's connected with bootstrap aggregation. Bootstrap aggregation is the same as bagging. So we are constructing different decision trees, then somehow trying to average. And you know that when you have some random observations and coming from different distributions, and finally when you are calculating the average, actually the final distribution has smaller variance. So the idea is to construct different decision trees and that the final prediction take as an average result of those decision trees. And bagging is applicable not only to decision trees. Bagging is universal approach. When you see some approach which has very big variance, bagging will always help. Just perform bootstrapping on your observations, construct the same several copies of the same method, and the final prediction should be the average of those separate models. Two advantages that we have in case of bootstrapping and averaging. So as we discussed earlier, bootstrapping is performing some training data sets, multiplying our training data sets. So when you have only one training data set, bootstrapping is giving you new ones. So you have different training data sets coming from the same origin. And when you are just averaging based on different training data sets, you are just reducing variance. This is just a universal interpretation of bagging, which is actually applicable to different approaches. And in case of decision trees, it's becoming very powerful powerful approach. And here we have description of why we are reducing variance, because when you have n independent observations, Z1 and Zn, all coming with variance sigma squared, coming from the same distribution, when you are calculating the mean, then you are getting the corresponding variance sigma squared over n. So this n is helping us to reduce the variance. So when you have decision tree unique comparing with the Bayesian approach, you understand that you are decreasing your variance of the final prediction by this n factor. One problem that we are actually encountering, the problem is that Bayesian is becoming very complex, because instead of one decision trees, you are going to draw 100, 1,000, 1 million different decision trees, and then somehow average them. And usually you need to have a lot of training information in order to end up with powerful approach. So here is description. This big B is actually the number of different classification or regression trees that we are using. So you understand that we can apply this approach both for classification and regression. When we are saying that we are averaging, we actually mean regression trees. But in case of classification, we perform actually the same thing. We are getting different classification trees. Each classification tree is giving the prediction. Then you are calculating the percentage of different predictions, the overall, and the maximum prediction you are getting, you are taking as a final prediction. And in this case, what is interesting in case of Bayesian, some interesting observations. It's very difficult to mathematically prove, but however, based on some practice, we have these kind of observations. The first observation, then there is no need to prune the trees when you are doing Bayesian. You are just growing very deep, very big trees, because you know that finally you are going to take the average. That is why there is no need to prune them. Because even when individual tree has high variance, eventually when you are averaging, you are somehow decreasing this variance. But instead, when you are drawing a very big tree, you have low bias, and this low bias will help you eventually. Because we know that we were struggling against variance by this averaging process. So this is, I don't know why the same slide copy pasted in any case. So this is how Bayesian is working for regression. So you see you have different decision trees. Big B is showing the number of overall decision trees that we have. X is standing for a specific observation. For this specific observation, different decision trees are giving us different predictions. Then we are taking just the average of those predictions and returning the final average as a prediction of a Bayesian. Very simple idea. And the same is for classification. You see here, as I described, majority vote. So different decision trees are predicting different classes. If you have 100 different decision trees, then you have 100 different observations. You are just calculating the percentage of each class within these predictions. Then you see which prediction is coming with the biggest percentage. You are taking this as a final prediction, which is again very, very natural. Then one interesting observation we have here, how we are actually using this observation for cross-validation. This is known as out-of-bug error estimation. So this is very natural way of doing cross-validation. while working with Python codes, I will show you, because in Python we have the corresponding output. Instead of doing cross-validation, we can just calculate this out-of-bug error estimation. We will discuss it later. So here we have a small description. You can read it, because in case of bootstrapping, when you are doing when you are randomly selecting some observations with replacement, you are getting a lot of different observations that you didn't use while you were constructing your decision tree. So those observations you can select as a test data, and exactly the tree that you just constructed, you can apply to those test observations, then average the corresponding predictions and return as an estimate of your test data, and this is known as out-of-bug error estimation. So this is actually identical to Lee-1-out cross-validation, but without any additional procedures. This is one interesting idea that we have in case of bagging of decision trees. And here's some comparisons here. So we have original tree. You see this dashed red line. This is actually test error for original tree. And then we have two different curves for back trees. Let's try to understand the difference. Here, the green line represents a simple majority. Okay, I recall what kind of problem we have in case of classification. Very interesting approaches. Assume that you are trying to apply decision trees for classification. Finally, the prediction should be some class. There are two interesting approaches. When you are trying to compare them, it's becoming very interesting. Assume that you are returning some classes as the prediction of each decision tree. It means that finally, when you are trying to understand which class to predict, you are just calculating the majority vote. So if you have, for example, 2 red points as a prediction with 100 black points, of course, you are returning black points as a final prediction. This is known as majority vote. For each class, you are actually calculating the percentages, and the biggest percentage you are returning as a final prediction. But this is not only the one approach that we can apply. Remember that in case of classification, instead of returning labels, we are usually returning some probabilities. And we have cutting point. When this probability is bigger than 0.5, we are assigning to one of the classes. When it is smaller than 0.5, then to other class. So sometimes it can be very reasonable, instead of returning the labels, just return the corresponding probabilities. Assume that decision tree is returning a probability for a specific observation. Now you have 100 different decision trees. You have 100 different probabilities. You are just calculating the average of these probabilities. In this case, you are working with numerics. That is why you can calculate the corresponding average. Finally, you are getting an average probability. And then for this average probability, just checking, is it bigger than 0.5 or is it smaller than 0.5? And finally deciding to which class you can assign your observation. Two very much comparable results. Sometimes they are giving totally different predictions. But in this example, you see actually that for these particular data, it's not important which kind of data we are here using, but it's just an observation that here we have red and we have this green color, you see, and purple line. So green line represents a simple majority vote approach. So when you are calculating the corresponding percentages, and the purple line corresponds to averaging the probability estimates. You see then when the number of B is tending to infinity, actually these two approaches are comparable. They are actually the same. But pay attention then for specific applications for specific data then can be totally different. However, these are just observations. Remember that you have two choices: work with probabilities and work with the corresponding labels and then calculate perform majority vote. It depends on your data, on your application, but this is just an interesting observation. Then here we have another regression example. The red line represents the test mean sum of squares using a single tree, and the back line corresponds to the bagging error rate. So this is showing how bagging sometimes can be better compared with the original tree, but pay attention that numbers are not giving you a big difference. You see that the original tree is almost around 30. This is giving you mean sum of squares. This is MSE, while the average for bagging is 20. So of course, the numbers are not, the difference is not very big, but you understand that the difference in percentages is something like 10 is 30% of 30. So we have 30% better prediction accuracy here, which is in some cases can be rather important. Disadvantages of bagging, as usually, we have very powerful approach, very nice working, but we need to discuss about some disadvantages. Again, very important observation. Remember, interpretability versus power of prediction. We have improved power, but unfortunately, the final result is very difficult to interpret. Why? Because we don't have 3 as a final result. We have 1,000 different trees, then we are averaging. Each individual tree in this case is useless. You cannot just understand how this tree is describing your data, because within 1,000 different trees, one tree is just nothing. That is why, again, we have the same logic. We have increase in power, but we have decrease in interpretability. When you are showing the results predictions in case of bagging, there is no tree that you can show to someone to explain how bagging is working with your data. So we have actually interpretation problem here. So you need to decide if you need interpretability, then you are applying single decision tree. If you need power of prediction for regression or classification, then you are just applying bagging. This is how you are choosing different methods. Any questions if you have?
Excuse me, if we have n observations, so we would have n trees, n different trees. I didn't understand how we choose the number of trees. Is it
Number of what?
number of trees?
Number of trees. This is parameter that you are just selecting based on cross-validation.
Okay.
You see in this example, for example, here you have 50 different back trees, then 100, then 150, then 200. You understand that starting from 50, there is a saturation.
Mhm.
These errors are becoming very stable. So you are actually applying cross-validation, tuning this parameter B, but you know that there is no reason to take very big trees, but for different data, the number can be different. As usually, cross-validation. Assume that this big B is your tuning parameter. You need to select the correct number for big B. Cross-validation will help you to understand if the errors are decreasing, then you are increasing B. When you see some stabilization, saturation, then you are actually stopping the procedure.
Okay, thank you.
And you always can compare with the prediction that you have for a single decision tree. You have this red dashed curve. you have the corresponding error 0.3. Then you can apply the corresponding bagging and see, is it reasonable to apply bagging or no? You see that this value 0.2 is the best that you can get based on the Bayes classification. So our backtrees are very close to this Bayes approach. But in any case, when you are comparing with the original tree, the best possible should be 0.2. Here you have 0.3 with original tree, and maybe 0.15 for this back tree. You need to decide, is it reasonable to apply bagging, or you can just go ahead with this original tree? Because sometimes it's also possible that bagging doesn't improving your approach. It's also possible. This is not a universal approach that just you can apply to every data set and get some reasonable results. So that is why always, as usually in machine learning, you have different choices. You are just applying cross-validation to see which approach is the best for your application. And of course, you have interpretability versus power of prediction. You have maybe some lack of resources. That is why there is no reason to apply flexible and powerful, very complex approaches. Maybe based on your resources, one decision tree is more reasonable and feasible for you than just to do bagging. Because in any case, when you have rather big data with many different observations, in case of bagging, boosting, and random forests, you have many different parameters that you need to tune. And usually it is taking rather a long time until you will find the optimal values for these parameters. And last time we even tried to do some bagging and boosting during our midterm, and we took rather long data, like 400 different observations. And in many cases, we encountered some problems because just tuning of some parameters took 30 minutes. So you need to understand that decision tree you can construct during some 10 seconds. Is just very fast, even for 4,000 different observations. But for bagging, boosting, as you have many different parameters that you need to tune, you can end up with something like 30 minutes for the same 4,000 different observations. Last time during midterm, as I can remember, we were using 10,000 different observations, but then we gave up with it because it's impossible to tune one decision tree 30 minutes, then understand that you have a problem there. You need to start everything from the beginning. So take into consideration that this power of prediction is coming by some cost, by some resource utilization. So I think if you don't have any further questions, we will go ahead with random forest next time. So for next time on Friday, we will continue with these decision trees, and we'll end this story because we have random forest and we have boosting, two very small topics. Then we will jump to some Python codes. We will see how all those things are working in Python. And if you have some interest in these decision trees, then just try also to use R programming language capabilities if you know R programming language, because as I said last time, in many cases, R has much more powerful capabilities than sklearn. Maybe it is easy to understand because individual trees are not so much popular when you are comparing with boosting and with other things. That is why the implementation is rather poor. We are using it just an lecture material to understand how the decision trees are working. But as they have rather poor prediction power, that is why people are not going ahead implementing much interesting codes here. And that is why R is, in this case, is much more powerful because R programming language is somewhat more obsolete and ancient programming language compared with this Python. Okay, guys, if you don't have any questions, Have a good day. We will meet on Friday. And today, yeah, by the way, you have PSS. So Tigran will put the corresponding link. You will go across all our classification approaches, LDA, QDA, logistic regression, KNN. Just repeat all those things because on Saturday we will meet during our midterm. Have a good day. Bye.
Bye. Thank you.
Goodbye.
Bye.